So today it's my pleasure to welcome Jerzy Lewandowski from the University of Warsaw, Uniwersytet Warszawski, who is going to tell us something about horizon equations. So I'm really looking forward to this talk. Let me remind you that this talk is being recorded, like all our talks, so you can watch it later on our YouTube channel. Jerzy, please go ahead.
Good afternoon. It is a pleasure to be talking to that interesting audience. My talk is about horizon equations, so I will maybe start with definition of what kind of horizon will be discussed. So let us, at the beginning, I will be even quite mathematically precise, so you will see precise definition, and later maybe I will relax a little rigor, and then we'll be able to go faster. So now I'm discussing non-expanding horizon as an unembedded surface. So there is no space-time, it will be just the horizon itself. So non-expanding horizon is a n+1 dimensional manifold. This manifold is endowed with a symmetric tensor, and this symmetric tensor has signature 0 and pluses. So this is basically a geometry of a null surface, or these days you may refer to it as some Carolian structure, perhaps, or it has something to do. But moreover, in the case of non-expanding horizon, we are also, okay, so this 0 means that there is a degenerate direction, which means there is one direction distinguished, which is annihilated by this tensor. And we often choose a vector field which takes values which is tangent to this direction, and then I will call it L. Of course, this choice is not unique, and it will be always discussed and taken into account. And furthermore, non-expanding horizon is furnished with a covariant derivative. So this is a connection on the tangent bundle to this surface. This derivative is assumed to be torsion-free. I hope that this notion of torsion-free is clear for everybody, but this is the usual assumption we make about connections. At least often we make this assumption. I'm not saying that there are no interesting torsion to connections with torsion, but here we're assuming it's torsion-free, and we are assuming it annihilates this tensor G. Okay. And now you might think, okay, so if this G was not degenerate, so if signature was either all pluses or maybe some pluses and some minuses, but no 0, then such connection, such covariant derivative would exist, and it would be unique. We could even calculate explicitly its corresponding connection components from the metric tensor. Now, if this metric tensor is degenerate, then you might think that there is ambiguity in constructing such a connection, and this is true, that there is ambiguity. However, it turns out that there is also an extra constraint which normally doesn't which normally it doesn't exist, namely, and this is a nice observation, that if you consider any vector field tangent to this horizon that takes values in this distribution of those degenerate directions, which another so just null, then this is a symmetry of the tensor G, of this degenerate metric tensor. Obviously, a priori, if you construct such surface, you might start construction with G, which doesn't have any symmetry like this. But then you are not going to find a connection. So So this connection exists only if this is true. And if this is true, then it is not difficult to actually show that this connection, there exists class of connections D which satisfy this. This is not a very difficult result. This is one-line proof. However, it often surprises geometers and mathematicians, and some. So I like to emphasize this at the beginning. So this is our abstract definition. I mean abstract in the sense unembedded horizon. I will also use indices, and this is the index convention. So G is going to have two indices, L will have one index upstairs, the covariant derivative has one index, and for the horizon we use little Latin indices. Okay, so now what are ingredients that define this structure? Okay, so the interesting ingredient is the following. If we consider covariant derivative of this L, so L is this degenerate vector. I mean, any choice of vector field that takes values in this degenerate direction, then certainly covariant derivative preserves this direction. So it means that it is proportional to, as a tensor, to again to this vector times some one form. And this one form has something to do with rotation of horizon. However, not exactly this one form, but the exterior derivative of this one form is actually this invariant description of the rotation. So that's why I tend to call omega a one form potential, because this is one form potential in the same sense as vector potential in electromagnetic field, or gauge potential for gauge theory. But in this case, it is a part of a connection, but by itself, it is also a sort of connection. Now, there is that freedom in choosing this null vector. I will often call L null if it's parallel to the degenerate direction, and then omega transforms in this way. So now you can see why I tend to think of this as potential. Another ingredient is a tensor that I call transversal expansion shear, but this name is meaningless at this point in the case of an embedded surface, just a name. And it can be constructed as follows. Consider given L, consider a function that we may say that this V is parameter along integral curves of L corresponding to L, right? This is the meaning of this equation. And then if we take the second covariant derivative of V, that defines for us this transversal expansion shear. So of course, this shear, it depends on choice of this function. It's easy to write also some general transformation, but I will not bother you about this transformation at this point. When it becomes relevant, then I will bring it up. Now, an element of rotation one form potential is surface gravity. So surface gravity is a contraction of this vector L with rotation potential. And in other words, this is self-acceleration of this null vector, which I chose. Since I choose this vector L was chosen arbitrarily, this surface gravity here is also pretty arbitrary. I can make it 0, I can make it arbitrary function. So this is not this surface gravity which we have in mind when we consider a black hole, because in that case, our L is distinguished. In this case, L is not distinguished yet, so this surface gravity, it depends on L, and it can be arbitrary function. So we can assign this. So given a slice V equal constant that will be n-dimensional, we can identify this slice. Maybe a more a covariant notion is if we consider the set of null generators of this surface. Well, so probably some global assumptions should be made for such a quotient to exist. But if it exists, or if it exists locally, then those ingredients which are defined, they induce on this set of null generators, or in other words, on this transversal section, they induce the following data. So they induce a metric tensor, which now is a genuine metric tensor of signature n pluses. So now it's not from the point of view of this. So this object is one dimension, has one dimension less than the surface, and the horizon, and we drop exactly the null direction. So for this reason, this metric here defined on horizon, this degenerate metric, now defines a proper metric tensor on this slice, and the one form potential defines a one form on this slice, and this tensor S defines also a pullback to this slice. And actually these are the characters of the story, which I will be telling you. Most often we will use those guys will be subject to some interesting equations. Are there any questions so far that would also prove that you guys exist and are listening to me? Okay, I can see you, so that proves.
There is no conclusive existence proof, but
okay.
But there are conjectures.
Okay. Okay, so now let us embed this surface. So an embedded horizon is n plus. So the horizon is embedded in n plus 2-dimensional space-time. And then it becomes just a codimension 1 null surface. Now, then the ingredients which I defined, and of course I'm assuming that this covariant derivative, which is defined, which is that furnishes this horizon, is consistent with the spacetime derivative, and it is just the restriction of the spacetime derivative to this null surface. And now if I for the surface gravity, which I already defined, and for rotation potential, if I write this equation, then it turns out that there is a nice geometric identity which relates the gradient of surface gravity with Lie derivative of rotation 1 form potential, and with the external Ricci tensor contracted with the null vector and pulled back on the horizon. So this is one equation, and usually we assume, so this is space-time Ricci, and usually we make some assumptions on positivity. We assume Einstein equations, either vacuum or with matter, but if matter satisfies positivity, it is classical matter, so it satisfies positivity assumptions, then usually this term is just 0. And then as you see, the gradient of kappa of surface gravity is Lie derivative of omega. So if one of them is, if omega is Lie dragged, then kappa is constant, or if we choose kappa to be constant, then the right hand side is satisfied. So this is generalized Zero's law of black hole thermodynamics. And now this, what I called this other ingredient now, this tensor S, it can be related to transversal null vector, and it is just the Lie derivative of space-time metric tensor in this transversal direction and pulled back on the horizon. So this is now after embedding this part of data, it gains this meaning, and so each slice for each V gives us metric tensor. This metric tensor is slice independent. We can also make omega slice independent by choosing kappa to be 0, for instance, and S is the only part of the data which is dependent on V, which means on choice of slice. So the only V dependence now is in this in this S. And we can again now write some geometric identity which relays the intrinsic data with spacetime. And this identity is here. So here is the spacetime Ricci tensor pulled back to this slice. Here is the intrinsic Ricci tensor of the metric induced on slice. And here is the omega and the tensor S. So you can see that such equation has, from this equation, you can easily integrate this equation, and it gives and determines evolution of S given some initial data on a single slice. Okay, now what is the meaning of an embedded non-expanding horizon? So actually the meaning is that we can call it a killing horizon to the zeroth order. Namely, if a non-expanding, if this non-expanding horizon is embedded, then there exists a choice of this vector L, and there exists, or perhaps it is true even for every L. I'm not 100% sure at this point, but certainly there exists a choice for this L, is such that there exists extension of L to spacetime. So let's call this extension T, such that the killing equation is satisfied. However, it's satisfied only on this surface. So that's why I call it killing horizon to zeroth order, because to killing horizon would mean that this equation is satisfied everywhere, but it is satisfied. So for every non-expanding horizon is a killing horizon to zeroth order. But we can also assume it is killing horizon to the first order by making this assumption. And so then we require a little more. And then it restricts the freedom in choosing this vector, null vector L. And now you can see if this is true, then certainly the right-hand side of this equation is true. And then the surface, it is already guaranteed that surface gravity is constant. So we have now the proper version of Zero's law of thermodynamics, that surface gravity is constant on our horizon. Okay, very good. So if something is constant, then this is either zero or not. And so let us start with the case when kappa is zero. So when kappa is zero, that means that T is just tangent to the null curves, the integral curves of T are exactly geodesics. So they are geodesics, even including parameterization, finely parameterized geodesics. And now, okay, so now let us assume, we have to assume something more. So suppose that surrounding spacetime satisfies the Einstein equations with cosmological constant. I think it's enough that those equations are satisfied just at the horizon. They don't have to be satisfied everywhere else. So it's enough that they are satisfied on the horizon. Then it turns out that this implies interesting constraint on this data, which defines the horizon, namely one of the on the metric Q, on the metric GAB, and one form potential. So those two were originally defined on n+1 dimensional surface, but actually they are defined on the space of null generators. So they are defined on dimension 1 lower surface, or in other words, they are defined on a slice. And actually they are slice independent. So we obtain, so if we consider the n-dimensional space of the null generators of this surface, and then it is there we have this induced metric tensor and induced one form potential, and the two of them, so now ignore S at this point, and the two of them satisfy this beautiful equation where this is the covariant derivative defined corresponding to this metric n-dimensional metric tensor, and this is the Ricci tensor of of this metric tensor. So we now are projected to n-dimensional space of, so space-time was n+2 dimensional, and now we are on n-dimensional space, which can be thought either as a section of slice of horizon or the space of null generators. And then globally on this space, there is satisfied such an equation. This is beautiful equation. It was probably first met by pioneers like Heidsieck. Eisenberg and Moncrief, they spell out this equation in their work. However, they consider slices which have shape of torus, and as I will explain in few slides later, then the only solutions are trivial, so they didn't use this equation. And then I rediscovered this equation with my colleagues, and later with my PhD student, we tried to solve this equation in four-dimensional case, and then we discovered that actually the only solutions that exist, if we assume axial symmetry at least, are the extremal Kerr, and then we call it uniqueness of extremal Kerr, local uniqueness. But now this equation is famous, and it has a different name. I will come to this at next slide. And there is a living review by Kunduri Lucchetti, which contains a lot of results on this equation. However, those results which I'm telling you now may be not included in this review. Okay, so now so what can we do with the solution to this equation? So suppose that somebody gives us some n-dimensional manifold endowed with a metric tensor and the one form, and that the parameter lambda, and that they satisfy this equation. Okay, when nabla is just the covariant derivative corresponding to this metric G, and this is the Ricci tensor of this metric G. So now what I can do is I can build the spacetime in the following way. So I take Cartesian product of S with two more lines. So my manifold is n+2 dimensional, and then I define a metric tensor on this n+2 dimensional manifold in the following way. First, I pick this metric tensor which is given, and then there are two more coordinates, u and v, which correspond to those factors r and r. So you can think that u is a coordinate in this first factor, and v is a coordinate in the second factor. And then I add to this part to this tensor. So of course those coordinates which are defined on S, they are just naturally pulled back to the Cartesian product. And then there is a sort of ansatz or definition how to determine from GAB and omega the coefficients, the other coefficients of this metric tensor. So for instance, this coefficient is quite simple. It is just v times omega, and omega doesn't contain any v. Omega depends only on x's. Whereas this coefficient is a little more complicated. It contains divergence of omega, square of omega, and this parameter lambda. And now the statement is that if omega and g satisfy this equation, then this metric tensor satisfies the Einstein equations with cosmological constant. And incidentally, this S defined in the previous transparency is just identically zero for this. Now, the horizon, because there should be some horizon, my talk is on horizons, right? So the horizon is the surface V equals 0. Okay, and it is extremal with respect to the vector field ddu. However, it also admits the spacetime admits another Killing vector, vdv minus udu, and with respect to this Killing vector, this horizon is not extremal anymore. So this is a Killing horizon that is extremal and non-extremal at the same time. And such geometry is called near horizon geometry. And it is used by people for some other reasons I'm not going to talk about, but they make it very useful and important in some areas of theoretical physics that take place in space-time.
Jurek, did you define what is an extremal horizon, or everybody knows this?
Sorry, I here. So I turned at some point to the case when kappa is 0, and then I use the power of title of my slide, extremal killing horizon. So in this way, I implicitly I thought I defined extremal killing horizon. So killing horizon is called extremal. So if this is a killing horizon to the first order as here, then kappa is constant. And then if kappa is 0, then we call it extremal. Okay. So if I didn't define earlier, then hereby.
But, don't you have a more conceptual definition? I mean, kind of a physical definition.
The physical definition is that for spacetimes that admit horizons, horizons are usually given by a root of some polynomial. And but when roots are single, then then kappa is not 0. However, kappa vanishes whenever two roots run together. And in physics, we usually define the domain of interest, of our interest, in such a way that we are interested, that physically interesting cases are where roots are different. And okay, so if we consider the Kerr spacetime, then either we have two different roots, and then we have two different horizons with kappa different than 0. Then we have this case when kappa is 0, and then we don't have any other case. So it means that something is maximal in this case.
Yeah. But, so what is this polynomial whose roots you are considering?
Well, this is the norm of. So you can, well, you want to know too much. You can come to my lecture on GR, and I can tell you. Well, usually this is we have two-dimensional orbits of null symmetry, and then the geometry of those orbits is either space-like or time-like, but there are some points where it is degenerated, and then those points correspond to those roots. Well, I don't know. I can, well, if it is really important, I can write an example. Sorry, but I don't know why. Okay.
Yeah, it might be useful to.
Okay, so I can write an example. This polynomial may look like this: 1 minus 2m divided by r. That would be the Schwarzschild black hole, but then there is only one root. So we don't have extremal case. But if we consider with cosmological constant, then it would be lambda divided by 3 times r square. So then if we multiply this by r, and then we obtain this polynomial which I was talking about, and this polynomial has two roots. One corresponds to cosmological horizon, one corresponds to black hole horizon, but sometimes those roots run together, and then we have extremal case. Okay.
Yeah, thank you.
Okay, thanks. So
are you happy, Jan, or you wanted to know more?
So this is in the case of so-called Kotler solution. I think the person who first found those solutions was Kotler, but people usually call it Schwarzschild de Sitter or anti-de Sitter. But if this is anti-de Sitter, then you don't have those roots. So but it's better it's Schwarzschild. Okay, thank you for the question. Thank you for the question. I hope it clarifies a little what I'm talking about. I hope my answer clarifies. Of course, question is perfect. So what I was talking about, so I was talking about that if we just start with this equation, which may be considered just as interesting equation on its own, and we find a solution, then from this we can construct a solution to Einstein equations. And since still it's not clear whether all the solutions of this equation are known, you still have chance if you, after my lecture, find a new solution to this equation, you can use this ansatz, and then you can announce that you found a new solution to Einstein equations. And in this solution, the surface V equals 0 is non-expanding horizon, and it is what I call extremal non-expanding horizon and non-extremal at the same time to make it more difficult. Okay, but let us go on and let us now assume, okay, so when you are doing usual mathematical relativists, they don't consider killing horizons to some order. They just consider killing horizons, and then this is a killing horizon to all the orders. Okay, but if you are pedantic and want to see what order by order in what way your what equations are implied by which order, then you can assume that it is killing horizon to the second order only, which means that the killing equation is satisfied, that Lie derivative commutes with covariant derivative, and Lie derivative also kills the Riemann tensor. So now, if we assume this, then it turns out that previously I defined this tensor S. This was this transversal shear and expansion. It turns out that there is also a linear equation, partial differential equation of second order on this S, on the background, omega and G, on the background defined by a solution to this equation. So now we have a solution to this first equation I discussed, and on this background given by this solution, we have just a linear equation on certain symmetric tensor. And this equation is quite tricky because it has a large family of gauge transformations which should satisfy this. So there should be non-trivial solutions which correspond to just gauge freedom. So you can see this gauge freedom is quite rich, and all solution like this is also a solution to this, or every S like this is a solution to this equation. So in this way, the assumption that killing horizon is extremal imposes a constraint and it also imposes a constraint on S, which is quite non-trivial. Okay, so now, and moreover, there is something else. We can also consider this killing equation to higher orders. So we may assume it is satisfied to infinite order, and then we bring more unknowns, namely we bring derivative of initial data in transversal direction. However, we also bring new constraints, and in usual case, those new constraints would just determine the new unknowns. But if we are assuming this killing symmetry, which is not only Einstein equations, is also killing, is also an additional assumption, then it's not clear whether those new constraints are actually all solvable. So that is a interesting and non-trivial obstacle for existence of extremal killing killing horizons. And since this is also something else you should know, that even though we know about black hole uniqueness theorems and so on, but extremal horizons are always a weak part of those theorems. So mathematical relativists would prefer to know just by inspection or more or by individual examination of what are possible extremal killing horizons. So this kind of results is problem is relevant for the uniqueness of extremal horizons. Okay, now I would like to
excuse me, killing horizon. What is the meaning of killing here? So a killing horizon is a horizon with an extra symmetry, or what?
Okay, I'm explaining. So okay, so if there is in spacetime a vector field, which is a killing vector field, meaning this equation is satisfied everywhere by T. And if there exists a null surface such that this killing vector, so the killing vector is a vector field which satisfies this equation everywhere. This is killing vector. Now, second, if there exists a null surface such that killing vector is a tangent to this surface and null, or in other words, orthogonal to this surface, then the surface is called a killing horizon. In our case, so you can see that if such killing horizon exists, then it is what I call, then it certainly satisfies my definition, because in my case, I only require that this killing equation is satisfied on the horizon. And it also is a killing horizon to every order, because then if I consider the derivative in transversal direction, then then this Lie derivative kills not only metric tensor but everything, but it also kills well, maybe it also kills all the derivatives of the metric tensor in transversal direction. So this is symmetry not only of metric tensor but also of all the derivatives of metric tensors in transversal direction. So killing horizon is some strong property, but this is the most usual case of non-expanding horizons. However, there are examples when such null surface is not a killing horizon, but is not expanding horizon. It is a non-expanding horizon, like in case of Robinson-Trautmann solutions, for example, of the Petrov type 2. Okay, now I would like to turn to four-dimensional case, because that case is even more interesting, because there's more we can say. Okay, so even if you didn't understand, were completely confused by my talk thus far, you have one more chance to catch up. So consider a two-dimensional manifold. Suppose that this manifold is equipped with a metric tensor and a one-form. Then the equation which I consider now is this equation, where K is the Gauss curvature and lambda is a parameter. You may, if you allow, I will call it cosmological constant. However, in this two-dimensional case, there is no cosmos, and it is meaningless. This cosmological, however, it's related by some embeddings to cosmological. So this is a beautiful equation. What we can do, we can play those cheap tricks, like we can contract indices, then we can integrate, and then after this integration, we can use Gauss-Bonnet theorem, and we can find the following inequality, that there is some inequality between the topological characteristics divided by the area and the cosmological constant. Okay, so So if cosmological constant were 0, then this would mean that this just has to be bigger or equal than 0. If there's cosmological constant, then we have this inequality. And then we can, by looking at this inequality, we can see what is domain of values of those parameters which is still allowed. So for genus 0, all cosmological values of cosmological constant are allowed. If genus is bigger than 1, then only negative cosmological constant. If genus is 1, then also the same. And there is also a possibility of genus equal 1 and 0 cosmological constant, but then omega and k are trivial. So this is what this inequality is telling us. This is what this inequality is telling us. New equations. So it turns out that some important role is played by the following complex valued.
Jurek, I think, well, at least I have problems with hearing you. Is it just me?
Not you, not only you.
Oh,
I have the
okay.
same problem.
By using the area. So the omega is
the speaker is frozen now.
Yes, okay, also for me. Hello? Oh dear. I say the speaker is gone.
Right.
I have
Black
another
hole is
computer. Just a second. I will try from the other computer.
Oh, hello.
Yes.
So I'm up on my old transference.
Tak.
Although I could also, well, let us see. I'm sorry.
So you think it was just a computer rather than the internet at your place?
Okay, am I back?
You're back. I think we lost like a minute or two. At least I did.
Okay, I'm sorry.
So you froze.
Just let me make full screen.
Yeah. See. I have to go.
Okay, so I was discussing integrability conditions that follow from this equation. So so if you differentiate this equation several times, then it turns out that such complex scalar here is relevant, which is Gauss curvature plus I times the scalar, pseudo-scalar defined by this omega, and this parameter which corresponds to cosmological constant. And then we have second derivative. However, notice that it is contracted only with one element of this null frame, which means that this is the holomorphic. So if we use coordinates, then it becomes d upon dz, and there is no d upon dz bar. But of course, it's covariant, so there are also some other terms. So this is an equation which has some complex meaning. And actually, this complex meaning was used by us in the following that first we proved that this complex scalar is never zero. Well, if you are a physicist, then you ignore such small things. But if you are a mathematician, you know that sometimes it's good to know that equations doesn't allow some function to vanish. And then from this function, we constructed a vector field, just gradient of this function, and we decomposed this into holomorphic and anti-holomorphic part. And then we concluded that the holomorphic part of this vector is a holomorphic vector, which means that the components of this vector are also holomorphic functions. And then it turned out that on two-dimensional surface, there is a shortage of such holomorphic vectors. So a lot can be from this determined. And the conclusion was as follows, that suppose that we consider that equation on a two-dimensional manifold, and suppose that the Euler class is less equal 0, then the only solutions are k equal to lambda. So k is equal to constant. So the Gauss curvature is constant and omega is actually 0. So they are so there's no rotation here. If we believe that omega corresponds to rotation, then there is no rotation. So in this way, we actually proved that there are no interesting solutions of this equation, because those solutions are pretty easy to obtain. You just set here 0, here k for lambda, and this is a solution. No more solutions. Okay. So what is left is a sphere, and in case of sphere, there is this old result of ours that if we assume axial symmetry, then the only solutions are defined by extremal Kerr. So if we consider the spacetime defined by the Kerr solution, we find extremal Kerr when the parameter a equals to parameter m, then the corresponding horizon defines exactly this data and define. And we also generalize this to Einstein-Maxwell case. Some other people generalized to Einstein-Young-Mills case. There was this Kunduri-Lucetti, they here did a lot. We also consider the case with cosmological constant, and it seems more or less in the same way. So this, if you assume axial symmetry, then everything is straightforward. What is still unknown is existence of non-symmetric solutions. So there are arguments, for instance, that if you consider linearized equation, this is what Hrushel, Real, and Todd did. They considered linearized, but in another paper, not in this one. Or maybe Hrushel and Szybka and Todd, sorry. What they did is they considered linearized equation about axisymmetric solution, and they found that all the solutions are also axisymmetric. There are no non-symmetric solutions. And then they concluded that axisymmetric solutions are isolated from non-symmetric solutions. So maybe non-symmetric solutions exist, but at least they exist far from axisymmetric. There were some other results by Hrushel, Real, and Todd, which was if you consider the non-rotating case, but omega, not omega itself is 0, but just this exterior derivative is 0, then again you can prove that the only case is when k is equal to lambda.
Excuse me, what is NHG?
Okay, so sorry, I should have said. So this equation these days is called near horizon geometry equation, and it is related to the fact that this solution, which I described here, is called near horizon geometry spacetime. So because every solution of this equation gives a solution to Einstein equations, which is called near horizon geometry spacetime, this equation was named near horizon geometry equation. And these days it is so, this name is so common that I just started using it, and I didn't realize this. So thank you for asking. Okay, and okay, so the conclusion is that this equation on sphere, on one hand, it gives uniqueness if we assume of Kerr, if we assume axial symmetry, but we don't know if there exist solutions that are not axisymmetric, and if there exist, then this is a problem for some uniqueness theorems. That's why Khrushchev. But anyway, even as this result as it is formulated here, it was still useful for Khrushchev, Costa, and Heusler to fill some gaps in black hole uniqueness theorems. But they would fill those gaps better if we were able to answer this question: do there exist non-symmetric solutions? This is still an open question, even in 4 dimensions. Okay, but let us go on. There is also, but this was only first equation. And this equation is only on part of data which describes horizon. There is also another part, which is S, which is not involved here. However, if we consider Killing equation, which is extremal, actually here it should be to second order, then we also, I already discussed this, then we also produce one more constraint. And now if we take into account both constraints, then we can formulate the following result: that suppose S is a 2-dimensional sphere, suppose there are there's following data defined: the metric tensor, one form, and the symmetric tensor. Suppose that they are axially symmetric. Suppose that they satisfy this first equation, which I call new horizon geometry, and suppose that they satisfy the second equation, and the first equation is satisfied with lambda equal to 0. And if we also assume certain positivity, which has geometric meaning about trapping surfaces, then this solution necessarily corresponds to the extremal Kerr. So this is again some uniqueness result, but still we are assuming axial symmetry. We are not able to relax this assumption, which is somehow would be most interesting if we're able to relax. And there are generalizations of this result to Kerr-Newman, or I mean to gravity coupled with Maxwell field. And actually this result was due to this combination of my results with Tomasz Pawłowski and results of Lucietti and Lee. And also we wrote a paper with Kolanowski about this to clarify everything. Okay, so this closes the chapter on extremal horizons. Now I would like to turn to non-extremal horizons, but let us first negotiate how much time I have.
So there were some technical difficulties. So I would say like about 9 minutes.
Okay. And there were also some
announcements. Be precise.
There were also some interesting announcements.
Yes. So 9 minutes plus minus 1.
Okay.
So if you could finish like 5 past.
Thank you. Okay. Thank you. Okay. So this concludes the part on the extremal horizons. But what about non-extremal horizons? So now it turns out, let me recall. Okay. So now we consider again a surface that is killing horizon to the second order, which means the zeros order, first order, second order. But now we are assuming that this kappa, which is constant, that it is not 0. So since it's not 0, we call it non-extremal. Just because the 0 case we call it extremal. So suppose this is the case, and also that we have to assume something about the external spacetime. So suppose the Einstein equations with cosmological constant are satisfied by external spacetime. So now it turns out that there are actually the constraints which are imposed on our data are very simple. And at the end of the day, the metric tensor and the one form, which are defined on a slice of this surface, are arbitrary, while omega now is defined up to those gauge transformations. You can see this kappa. If kappa was 0, then this transformation would be identity. But if kappa is not 0, then we turn on this transformation. So if we relax extremality, then suddenly we have local degrees of freedom. Okay, so this is it. However, it turns out that our equation of extremal horizon still admits certain generalization. And what is that generalization? So so now let us turn to 4-dimensional case. So now space-time is 4-dimensional. Okay. So let me recall that when we considered extremal horizons, then we had this equation, but forget about this equation for a moment, but consider one of the integrability conditions. So it still makes sense to consider this integrability condition even for non-extremal horizon, because it's still well posed. And now it has a new interesting meaning. So if non-extremal Killing horizon to the second order satisfies this equation, which I guessed from the extremal case, and certain non-degeneracy condition is assumed, then the spacetime Weil tensor is of the Petrov type D at the horizon. So the Weil tensor has some algebraic classification, and Petrov type D, it means that of the 4 generically independent principal null directions, 2 are the same, and the other 2 are also the same. So it has only 2 principal null directions, and each of those directions is double. So we have a very nice geometric meaning to this equation, which we even in the case of non-extremal horizon. Okay, so we can go on and see what are properties of solutions to this equation. So it turns out that if we assume this equation so if we consider a sphere and we consider, okay, maybe first consider some surface of genus bigger equal 1, then again we find that there are only boring, simple solutions, which means maximal symmetry solutions, curvature equal to constant, and the rotation vanishes. And actually then this result is very similar to result of Hawking, that slices of connected components of horizon have to have spherical topology. So actually this is telling us the same if we assume that horizons are rotating. So rotating solutions to type D equations exist only on spherical sections. And now if we assume the same, consider the same equation, this equation on spherical section, then we find that we can find all axisymmetric solutions. And then just to make this complicated story short, we can find they are all embeddable in either non-extremal Kerr or de Sitter or anti-de Sitter, or in the horizon geometry or near horizon geometry spacetime. So this is again some property. So you can consider this as no-hair theorem. So no-hair property, that there are no other solutions than this. There's only 2 parameter family of solutions, which is parameterized by area and angular momentum. However, there is still problem with axial symmetry, but now we can do actually better than before. Namely, if we consider a bifurcated horizon. So what is bifurcated horizon? So now it applies only to embeddable case. So suppose that our spacetime admits 2 embedded horizons, and suppose that they intersect. Then this is called bifurcated horizon. So if we assume that we have bifurcated horizon, and so 2 intersecting horizons, and each of them is of the Petrov type D, then it turns out that they induce conjugate equations. So one of them induces such equation, and the other one induces very similar equation. However, this plus is turned into minus. And if two equations like this are satisfied simultaneously, then by commuting some operators, we show that this solution is also axisymmetric. So in this way, axial symmetry follows from the existence of bifurcation. So in this way, we can say that at least we know assumption which leads to the rigidity theorem, rigidity property. Okay, and now there is even one more direction of generalization. So you probably noticed that what I consider here as horizon, I don't particularly pay attention at global structure, but we may consider a U1 bundle, and we may provide U1 bundle with structure of horizon. So we don't have to consider a trivial bundle. We can consider a non-trivial bundle, for instance, the Hopf bundle. And then the structure which is necessary to discuss, I mean, this horizon structure introduces on the base space on this bundle, introduces a metric tensor. And it also introduces a connection, a U1 connection, which is obtained by our rotation 1 form divided by surface gravity. And we can impose Petrov type D equation on this data. And again, we can, so the only difference is that now the integral, previously the integral of omega was 0 because this was a closed two form on surface. But now this two form is not closed anymore. There is some topological charge, but there's also some surface gravity. So this is an arbitrary number. And then we find 4-parameter family of solutions to this equation. And then we look where those solutions are embeddable. And what we find is that there is a Kerr-NUT de Sitter family. This is a general, oh, now I can tell you what is this, what are those roots defined. So here you have this function Q, and horizons are defined by roots of this function. So in this case, this is fourth order polynomial. Okay, so those solutions which we found just by considering abstractly non-embedded horizon that has structure of a bundle, now we look for those horizons in spacetimes which are called Kerr-NUT and de Sitter. And maybe I now I'm not able to tell you the details. So maybe I can just tell you that we find those horizons here, but only for some specific values of cosmological constant. But then it means that there are only 3 parameters: a Kerr parameter, NUT parameter, and the horizon radius. So in this way we find only 3-dimensional family of solutions, whereas we have 4-dimensional family of solutions here. Okay, so this is a puzzle, but there are also. But in order to understand this puzzle, we actually construct globally those spacetimes. So this is something which we also solved while dealing with this problem. Namely, given this metric tensor has a one part which is very ugly. Namely, this one form is not really well defined on a sphere. This A doesn't have good dependence on sphere. So this one form is defined only at one pole. And a long time ago, Misner showed in easy cases how to extend it to another pole by bringing up Hopf bundle structure. However, okay, so we look for such structure in general, for general spacetime like this. So we look at structure of a U1 bundle, such that there is some metric tensor defined here, and spacetime has this natural form. And the result is the following: that we actually found all such globalizations of that local formula. However, it turned out that they always come with some distinguished killing directions which were not known before. But to make long story short, we found all globally defined spacetimes. So we have one spacetime in one coordinate system, another spacetime in another, and then we have some gluing conditions. But what is not, we can skip this. Okay, but this is the result. We obtain spacetime, which looks like this slice is three-dimensional sphere. And it is just Cartesian product with R. And here are, in generic case, there are our horizons. However, those horizons are not smooth at all. And only for some special values of cosmological constant, they turn out to be smooth. So now, so in this way, we sort of discovered that a horizon in a smooth spacetime doesn't have to define a smooth structure of a bundle of null generators. This is lambda less than equal 0 case. So we explained in this way why only some of those horizons are smooth and some other are not smooth. And where are the missing solutions? The missing solutions are in the accelerated Kerr-de Sitter space. Okay, so let me go to conclusions. Now, the question, can I go through those conclusions?
Very briefly, maybe.
Okay, so to conclude, we considered extremal horizons, and then there were some constrained equations, and one of those equations is very interesting on its own. It's called new horizon geometry equation. Still, there are some open questions about some basic open questions about the existence of solutions to this equation. In particular, in 4 dimensions, that they are not known. Next, we considered a generalization of this extremal equation, which is true, which can be applied also to non-extremal horizons. And then it turned out that the equation which we defined has properties that are known from global theory of black holes, like rigidity and no hair. So we found a local condition that ensures rigidity, no hair, and other properties known from global theory. So similar conclusions, but from different, obtained by different assumptions, different framework. And then we turned to horizons which have non-trivial structure topologically, for instance, Hopf bundle, and they come and they are related to Kerr-NUT de Sitter or anti-de Sitter spacetimes. And here there were some surprises that that only in some cases of Kerr-NUT de Sitter spacetimes those horizons are smooth, even though we were able to propose a globalization of this Kerr-NUT de Sitter anti-de Sitter spacetime for arbitrary values of cosmological constant, NUT parameter, and A. And this is actually an important side result of this research, that we found a nice, powerful generalization of Misner's gluing, and we glue spacetimes which either look like Kerr-NUT de Sitter, anti-de Sitter, but for some values of, so either they're similar to say Taub-NUT solution, but for some values of the parameters, they may have another meaning. For some values, they don't have any horizons, they don't have any singularity. They are solutions of Einstein equations with cosmological constant, and they describe evolution of universe that is three-dimensional sphere, which is not homogeneous. It only has two killing vectors, so three-dimensional sphere, but metric tensor has only two symmetries, and evolves from scry minus to scry plus, and they are globally hyperbolic. I'm not sure if there is anything wrong with those solutions. Probably this can be checked. Okay, thank you.
Thank you very much. Okay, so are there any more questions? There were some questions during, but now there is another chance. Yes? Jan.
Is there any relationship of this construction to the Pfefferman-Graham construction?
No, the other way around. We provide interesting exact examples for the Pfefferman-Graham gauge. So you can take our exact solution and you can turn it into, write it in Pfefferman-Graham gauge to some order, and then see what data is defined by our solution, and then you can, well, it may gives you some well, you can sometimes be surprised that there exists some. So what is surprising is that those NUT spacetimes, they were believed by physicists to be non-physical because they have those closed time-like curves. But on one hand, we have, if we go back here, if we consider such spacetime, you can see this is, so what you're asking about is this scry plus, and then we have this Pfefferman-Graham expansion around the scry plus. So you can see our solutions, they have very nice Pfefferman-Graham expansion. However, some of them develop this killing horizon, and then below, starting from this killing horizon, we have closed time-like loops. So we are not happy. But the Cauchy, from the point of view of the initial problem, everything was perfect. The initial problem was perfectly here. So they give examples of some initial data which develops horizons, but also they give examples of some initial data which doesn't develop those horizons. So I think they give examples of which have global properties, which have also opposite global properties. And you can wonder if there is some theorem behind this. So it's a very good question, and this is something we are thinking about exactly to understand the data which our exact solutions provide, and maybe some theorems about Pfefferman-Graham expansion that was more general.
Okay, and another question. Can one summarize your talk in the following way, that what you want to do is to construct solutions to the Einstein equation, and you do it starting from a horizon, which means something with a degenerate metric, or
partially. So the idea was that when we consider a black hole, the most interesting part of black hole seems to be the horizon. So the idea is, let us understand locally the equations satisfied by geometry on horizon, such that we don't do, so and usually after we understand this, then usually it turns out that there is a nice extension and we can build from this spacetime. But the main point of interest is local description, local understanding of spacetime at the horizon. Maybe black hole horizon, maybe cosmological horizon. Thus far, we don't see any difference. So we want to understand. In other words, we want to understand why the Kerr horizon, for instance, is so complicated. Why or the Kerr-NUT space-time, why is it given by so? I mean, well, on one hand, it's not really complicated because we have some rational functions, but on the other hand, you are not going to guess those functions. So what is the rule that makes those functions look like this? Why there are only two-dimensional families of black hole solutions? Why there is this rigidity theorem and no Kerr theorem, and we try to find local arguments for those properties, some assumptions which are imposed locally, and they have the same consequences as global assumptions about black holes.
So maybe a follow-up question to that. just very quickly. So is that a sort of ultimate statement? Like, can one say that, well, all the horizons have to be of a certain form, that they come from a given class of equations, and that's it? Or like, how general is is your statement, and well, you know, the state of the art?
Right. So, well, it seems to be some clever balance. So you can construct all non-extremal killing horizons just by setting arbitrary metric tensor, choosing slice, setting some metric tensor in one form, and from this free data you always can build locally spacetime which contains killing horizon, non-extremal killing horizon, and even satisfies Einstein vacuum Einstein equations of cosmological constant. However, if you consider those physical black holes like Kerr black hole, then it turns out that we have only 2-parameter or 3-parameter family of solutions depending on what parameters we introduce. So we want to find local reason for the fact that those globally defined black holes are set much smaller class than those locally defined black holes. However, it's not, we don't have any postulate that the black hole has to satisfy those equations. Well, extremal black hole has. So in case of extremal horizon, the answer to your question is yes. The equations which we consider are necessary for extremal horizon. But those type D horizon, well, this is just certain assumption we make about horizon, and then with satisfaction, we find that all solutions to this local assumption that they are also globally defined, embeddable in globally defined black hole spacetimes, or even not black hole spacetimes, because in case of those NUT solutions, those horizons, they are killing horizons, but they are not black hole horizons.
Okay, thank you. There is a question by Sumi Emada.
Yes, hi. I'm a stranger here. I'm Tasaki Sensei's colleague at Gakushuin. So hello. So it was a very interesting talk. Thank you. My question is that can you read off any information about the geometry of the domain of communication? I mean, the global structure from the near horizon geometry. I mean, is there such a program? And if there is, the next question is that, is there a way to figure out that it's the end is asymptotically flat or asymptotically Euclidean, so that you can connect your work with the so-called ADM theory? So that was my question.
Yeah, thank you. No, but this is this is interesting question. In our case, those parameters like a cosmological constant, they just enter those equations. On one hand, we know that space-time, depending on the value of this cosmological constant, has well, it's either asymptotically flat or asymptotically de Sitter, or so this scry is either space-like or null or time-like. But I didn't think about this, what you're asking, but it makes a lot of sense to ask this question.
Yeah, well, I mean, okay, so I personally, I studied the Penrose inequality. And then one of the things we did is that to study the Penrose inequality for the Einstein-Maxwell, where the so-called the Majunda-Papa-Petru metric, which is the extremal case for the Einstein-Maxwell, shows up in a kind of a rather interesting way. So I was trying to see the Majunda-Papa-Petru geometry in your talk, but I couldn't quite succeed it. But I suppose
actually it is hidden in one of the here I mentioned that there is some paper by Kerr-NUT, recent paper, when he studies those extremality equations, that actually he proves something about about those, so space, some sort of uniqueness theorem about those spacetimes you are asking. But it's not about the global structure. It's rather sort of uniqueness, whether there can be some other solutions of similar property. And I think that he argues that the answer is no, and that this is unique. But I skip this. I mean, I even didn't plan to discuss this in my talk.
Okay, thank you very much.
Yeah, but you're right. This is one of interesting examples of extremal horizon, which is different than extremal Kerr. And then the question also is whether we can have many solutions like this or only one. And I think that Kolonowski's paper deals with this question.
Okay, I'll look it up. Thank you.
Thank you for the question. Anybody else? Silence. Okay. I think we are done with the official part then. So thank you very much for the talk again.
Thank you. So what are attractions